Hello, this is another video about hierarchical metric flow on data graph. This is analytic tool for embeddings, and today I'm gonna show another function of it. I'm just writing it and testing. It's gonna show us how models are distributing resources based on our composition of prompt. So let's see one with common modes, and we get a report here, the last one, about our crows. So stupid phrase that crows, it crows for supper, and it has a score of 21. This score is based on metric. I use heuristics because this score is scalable, and I have a uniform scale on everything just because I use too much resolution. So it is some number, and it is number that is comparable. It is not absolute number. So now let's take another phrase and check it. So level clusters output, yep, here we go. And here we have another one. Next one, do hence do what I did. It is obvious, hence do plausibly. As you see, the score is very high. It depends on one simple thing, that emergent structure of embeddings have clustering for words that cause LLMs and other models to value your prompt on how much words that have low clustering. So short common prefix are noise, and long common prefix are specific words which have better foliation on meaning. So the value that is emergent in models, just because of how manifold is functioning, so where the labyrinth is leading into a lot of words or not many words, is valuing your prompt if readable or else. And prompts that are low scored lead to noise, hallucination, and similar stuff, because there is too many ways you can continue this phrase. Because if we look on the next token prediction need foliation. So if you have 200,000 ways of adding another word to a phrase, the model is gonna use random choice. It doesn't base much on context because choice is too big, and more foliation you have, so you have narrowed the manifold of the next word predictor. The less outputs are possible, and it looks like a model can narrow the answer, so it is more sure, and contrast between numbers are sharp. It is not about randomness and stuff. The procedure of the model is purely deterministic. Of course, model doesn't have this score, but it turns out it is the emergent. And the important thing about it is that people score phrase exactly same way. And it is used in cognitive testing, something very similar. So if we have some gibberish, like this is gibberish, and you use words that have a small and narrow cluster on long common prefix, people tend to have a first think about it. It is clever, and it is used in cognitive tests, so we know about it. And we distinguish people that are clever and more clever, let's say, by making this very plausible. So you make very plausible sentence, and the hack that it is wrong, it is hidden deeper and deeper until we get to the some specific logic, math, and stuff, where there is a lot of hierarchical and fractal layers of decomposition, and someone have to think about it for a longer time. It is useful for philosophy, for math, and other science where we communicate with language. It is completely unuseful for programming because there you have a deterministic machine that can run it directly and compile tell you you're wrong, and it doesn't tell you where you're wrong. It cannot be executed. Like, that's all. And the debugger can tell where did you something wrong or not. So the semantic for user language, like human spoken, not machine executed, is far different from synthetic languages, and this tool works on embeddings that are made on natural languages. Of course, they can include programming languages, but this is completely different story. The whole program that is decompressing the embedding to this set have 604 kilobytes, and 200 of them are pictures for those buttons you see. So it is not very complicated logic. However, math beneath it is heavy, and I have one hard disk that is mentioned only for this project. So unpacked 1.2 million tokens takes about 100 gigabytes of data, something like that, with 300 vectors. Vectors are not very important, the number of tokens is important, and it works on any vectorized data. Another thing you can be interested in that are reports, which I use to determine if the word is noise or not, where we have reports. Read up reports. Current reports. Here. Okay. So this file was created during the calculations, and it shows how many words are on the given levels. Those are overfittings and memorization here. Here we start with something semantics, somewhere around level 30. So it is 15 position of vectors. Of course, there are some words up the stream. So I found that way which word sounds clever, and it works for people. And if you use a lot of syntax, like comma, points, exclamation mark doesn't work very well. It is not recognized as a very specific syntax. It is expression. So if you use a lot of them, the phrase sounds clever, even for people, because models doesn't read minds. They read sentence and have a very good comparison to general language. So as you see, the most of the clustering start here. Human semantics base around here on level 17, between 16 and 18. Lot of words are ambiguous. They drop to 15, and if the word drop to 12, you only recognize word, but you don't know what it is referring itself. It needs a lot of other context word just to tell you what we are talking about, so which part of the word are interested for us. And I'm gonna publish some rants about it. Defoliation is very important. People use it in language. So for example, if we talk about isometrics, it is somewhere here. Very specific word, we know what we can talk about. If we, let's say, take some Napoleon or another Hitler, he drops here to 12 or lower, just because there is so much publication about it that model can't tell what are you referring to, and model doesn't have any imagination like you think you have. So the affiliation of the word need another context what you are referring to, history or conspiracy theory or some event or psychology or something, because there is too much documents and this word is connecting to everything else. What is very important for humans, they detect words that are at level 17 and operate them daily. They are sometimes using words at level 15, and when words fall below level 13 or 12, it is starting to disappear from language. The use case is stopped. The only way that people have to keep words running, it is redefinition. We're using this by connecting the word that is dying. It must be dying, otherwise you cannot connect it. You will just push it down. That is dying or is very narrow, like specific word in a specific trade, and redefine it by a new author that is starting to be popular. It is how the language is expanding. And in embeddings, if you have a dynamic embedding, so you have like a screenshot of that embedding of 100 gigabytes and the screenshot of the embeddings of 100 gigabytes that was 10 years ago, you can compare differentiation in the language, how it has changed. And if we have a model trained on language used on the beginning of the 20th century, and we compare to the beginning of 21st century, it will be completely different language, like foreign language. Those models will have hard time to communicate with each other. First, there will be not that many words in the historical parts, because there were no history which was future for them. That's obvious. But other words will have different meanings and different connections. And there are words you can tell that cannot change meaning, like chair or mother or power or authority. They have completely different meanings. And it also differ between subcultures. So this tool is able to measure such things and tell you if we can at all communicate and if given phrase sounds clever in given embeddings. So in given language, what phrase to use, what words in phrase to use to sound clever. And this is a clear metric. Yep, you can visit the web page, and if you are interested, so on. So the application is very small. However, the results are hilarious, and it allows me to make some exploit and test things on models. Thank you.